Welcome, students. We have started our chapter Force and Pressure, and so far we have discussed that push or pull on an object is called force. Force can cause the motion, it's the only cause of motion. And we have discussed that the unit of force is Newton, and it is a scalar vector quantity which having both magnitude as well as direction. So along with magnitude, the direction in which a force acts is also to be specified. Why? Because if the magnitude or direction of the applied force changes, the effect that is produced by force also changes. Say suppose um, uh, I'll explain it in this way. Suppose two forces are acting on an object. So two cases arise here. Either both the forces are acting in the same direction, or the forces are acting in the opposite direction, right? Let's take an example to understand this. Hey students, if two forces are applied to an object and two forces act in the same direction, then the resultant force acting on the object is equal to the sum of the two forces. You can also say that when two forces act in the same direction, their effective magnitude increases, right? This will become more clear from this example. Suppose there is a heavy box which one man can move only by pushing it very hard. Now, if two men push this heavy box and both of them are pushing it in the same direction, then it becomes much easier to move the heavy box, right? Why? Because when the two men apply their forces of push together in the same direction, the two forces add up, right? And they provide a much bigger force. And then this much bigger force can move the heavy box very easily. So here two forces are acting in the same direction. So the resultant force is equal to the sum of the two forces. Okay. Now let's take the another case. If the two forces applied to an object act in the opposite directions, then what happens? The net force acting on the object is equal to the difference between the two forces. You can also say it like when two forces act in the opposite directions, their effective magnitude decreases. Let's understand it by this example. Suppose again I'm having a heavy box and this box is lying on the ground, okay? Now let two men push this box, but both of them are pushing from opposite directions. Say one is pushing from the left side and other is from pushing from the right side, okay? Now assume that one of the men is stronger of the two, and obviously the stronger will apply a larger pushing force than the other man. We can say that the box then will move in that direction in which larger force is applied by the stronger man, right? Suppose if the man which is pushing it from the left side, he's applying his stronger one, he's applying the larger force, then the box will move towards left side, right? Because larger force is coming from that side now. So the box will move very slowly in this case, because the net force which is acting on the box is equal to the difference in the magnitude of two forces which is applied by the two men, and the net force is small then. Suppose if one person is applying a force of 10 newton and the other person is applying a force of 8 newton. Now the one who is applying 10 newton of force, they are applying in the opposite direction, right? And the one who is applying force of 10 newton, he will move the box towards his side, right? Because he is applying more force. Now what is the overall force, net force which is acting on the box? That is the difference of the two forces. Because obviously if one is applying 10 newton and the other is applying 8 newton, the force of 8 newton gets balanced, and what we are left with, 10 minus 8, we are left with force of 2 newton. That means the net force which is acting on the object is 2 newton. So that is what I told you, that if the two forces applied to an object act in the opposite direction, then the net force acting on the object is equal to the difference between the two forces. Now, if the two forces are applying to an object and the two forces are now equal in magnitude, but they act in the opposite direction. So this is third case, that if the both forces which are applying on an object are equal in magnitude but in opposite directions, then what would happen to the net force? The net force which is acting on the object is zero. No force will be applied, net force will be zero, no force will be applied on the object. Now, since the net force is zero, do you think that the object moves? No, the object does not move at all because the overall force is zero there. It remains in the same position. For example, if we are having two men and both the men, they are pushing a heavy box from opposite directions, but this time they are applying equal forces. One is applying from the left and the other person is applying from the right, but they are applying the same forces. Then do you think that heavy box will move? No. When the forces are equal, one is applying from left, other is applying from right, the box will not move at all, right? It will remain where it was. Similar thing happens in case of tug of war. This is a familiar example of this case of equal forces acting in opposite direction. Okay, in this game what happens, two teams of persons pull at a rope in opposite directions, right? Members of both the teams, they are trying to pull rope in their direction. Now tell me, if the two teams pull the rope equally hard, they are applying equal forces, do you think that the rope will move to any direction? No, the rope does not move in any direction. So at this point of time, two teams are applying equal but opposite forces because they are pulling on their side now, due to which the net force acting on the rope is zero and hence the rope does not move. Why? Because the equal and opposite forces applied on the rope cancel each other's effect, right? Because the forces are equal and opposite. So ultimately, only that team which pulls the rope harder by applying greater force wins the game. Otherwise, when the both are applying the equal and opposite forces, the net force is zero there. And we term these forces as balanced forces. So these forces are termed as balanced forces. So balanced forces are nothing but the forces which are equal and opposite in direction, and the net force acting on an object is zero, and in under the balance forces the object does not move at all. Okay, but in case when we are having a more force, suppose the team is now, one team is now pulling the rope harder, it's applying greater force, then obviously the rope will move to their side, right? So at that time the rope will move, motion is caused, but that is under unbalanced force because at that time one force is greater in magnitude, right? So when the body is under balanced force, object does not cause any motion, forces does not cause any motion, object will not move. But in case of unbalanced forces, the forces applied on an object are not equal in magnitude, as we discussed in the earlier two examples, where where two persons were applying forces, one in the same direction, and the other example was of when they were applying the forces in opposite direction but different forces, um, forces in different magnitudes. At that time the object was under unbalanced force, and that is why in both the cases object starts moving. Right, in both these two cases object starts moving because the forces were not balanced, because the net force, overall force, was not equal to zero. At one In one case the net force was equal to the sum of the forces which were acting on an object, and in the second case the net force was equal to the difference between the two forces, right? So this was all about balanced and unbalanced forces. Now see students, force, we cannot see the force, it cannot be seen, but yes, force can be judged only by the effects it can produce in various objects around us. So, force can produce the following effects. A force can change the direction of a moving object. A force can change the speed of a moving object. Say, for instance, if we want to see how force can change the direction of a moving object, you are familiar with cricket, right? In cricket match, when a moving cricket ball is hit by a bat, what happens? Direction of cricket ball changes and it goes in another direction. So, in this example, the force exerted by bat changes the direction of moving cricket ball, right? So, force can change the direction of a moving object. Force can also change the speed of a moving object. Suppose we are moving on a bicycle at a certain speed. Now, if someone pushes the moving bicycle from behind, what happens? Speed of bicycle increases, right? And it will move faster. But if someone pulls the moving bicycle from behind, now he's not pushing, he's pulling. You are moving forward, but someone is pulling you from behind. Then what happens? The speed of bicycle decreases, right? It will move slower. So force can change the speed of the bicycle. What was that push or pull? That was nothing but the force, right? Force can change the shape and size of an object. Suppose if we take a spring, we take a light spring and pull it at both the ends with our hands, what happens? Shape and size of the spring changes, right? So the force of our hands that change the shape and size of the spring. In fact, shape of a dough, that also changes on pressing with rolling pin, right? When we are making chapatis, then we press the dough with a rolling pin, we are actually applying the force now. So force can change the shape of dough. So force can change the shape and size of of an object. Force can also make an object at rest move. That means force can move a stationary object. Suppose we are having a ball and we place it, say, on a tabletop. Now we want to move this ball. Does it move by itself? No. Now we are gently pushing the ball along the surface of table. Now what will happen? You will see that the ball will begin to move, right? So the ball which was at rest begins to move when a force, when a push is applied to it. In fact, in football, right? If football is at rest and we want to move the football, we want to pass the football, what we need to do? We need to kick the football. What is that kick? That is nothing but a force, right? So force can move a stationary object. Force can also stop a moving object. Suppose you are having a rubber ball and that is placed on the table again. And now we are pushing this ball gently and it starts moving. Now place your palm in front of this moving ball. What will happen? You will see that while placing your palm in front of this ball, the moving ball comes to a stop, right? So basically, the palm which is held in the path of moving ball applies a force to the moving ball and force stops the moving ball. So ball, moving thing, it's comes to rest when a force is applied to it. In fact, in a football match, when goalkeeper dives or jumps up to save the goal, he applies a force to the moving football with his hands, right? And this force applied by goalkeeper helps in stopping the moving football and saves the goal being scored, right? So stopping of a moving football by a goalkeeper tells us that a force can stop the moving object. In fact, if a cricket ball is moving on the ground and if we will not do anything, do you think that it will stop automatically after some time? Yes, it stops after moving some time, it stops automatically. But why? We know that without force, the body which is in motion doesn't come to rest. Then how it stops? Then it means some force has been exerted there, right? And that is the frictional force. That is the force of friction of ground that stops the moving cricket ball. So we can conclude that force can produce the following effects. Force can move a stationary object. Force can stop a moving object. Force can change the speed of a moving object. Force can change the direction of a moving object. And force can change the shape and size of an moving object. Sorry, force can change the shape and size of an object. I hope this is clear to you. Thank you.